In this video, you'll find content related to Lesson 3.4 and 3.5. We're going to remind ourselves and use factoring to find how the zeros of the polynomials will help us sketch the graph. We'll look at the degree and the end behavior also to make sure we're correct. Once we know the degree, we're going to see how many zeros that function or polynomial should have. Lastly, we'll identify if those zeros are real or complex. So before we were doing functions, we would see something that might look like x squared plus 5x plus 6. Now, that's standard form. That would give us the y-intercept really nicely. But we began looking at factored form and encouraged you to be able to factor well, so you could always break it down into two parentheses or some sort of factor and find the zeros. That means you would find what numbers you could plug into each of those parentheses. So for this one, what number plus 3 would make 0? Well, that'd be -3. Now, if you didn't want to think about it in your head, you could always rewrite the factor itself and solve it to get x alone, and now we would have that -2 is the 0 of this factor. Now, using those numbers, we were able to put those on the x-axis because it meant that if you put -3 into this parenthesis or factor, you would get 0, and 0 times anything makes 0. So here's my -3. Same thing for -2. It's important to note that if you put -2 back into the original equation in standard form, this -2, if you put -2 in here and in here, you'd also get 0. It will make the standard or the factored form go to 0 because it's the same equation. So there is my second 0 or x-intercept, and I know it's a happy parabola. So first of all, the degree is 2. This is something we're used to. We're going to up this degree real soon here. The end behavior, remember we discussed that if you look at the highest degree, or the highest power, if you will, and it's in standard form, the sign out front and the degree will tell you how the ends behave. So in this case, because our degree is even, we know that the arrows or the ends of our function will both be ending up or ending down. Now that's to say we need to know which one it is by checking the first coefficient, and since there's a 1 there that we don't see, it's a positive 1. That means it's going to finish positively as x goes to infinity. So we might say as x goes to infinity, we know that there's a positive 1 out here, so we know y will also go to infinity. And that's going to leave it to be like this. That might be a little extra work for you because you're saying, well, this is just a happy parabola. I could have just drawn these arrows like you were saying and then connected them. That's a good enough sketch for now, but we just want you to remind yourselves that the degree, if it's even, they will either go both in the upward direction or both in the downward direction for end behavior. You could recall also, just a side note, that if it was an odd degree, your end behaviors would be in opposite directions, depending on your leading coefficient being positive, in this case, or negative. Now, for number of zeros, in this case, we see those 2 zeros. They both seem pretty real to me, and there are no imaginary ones. But let's kick up the power a little bit. The degree of this next function that we're going to look at is a 4th power. You'll see a 3rd degree power in your packet, and I highly recommend you try those examples. These go along with Lesson 3.5 with your example 1 and the triads. So the first example is not in your packet that I just did, just to refresh with the quadratic, but you'll find a cubic in example 1 on 3.5, and now here's another one you might find. We notice this is a 4th degree. I'm going to answer that right off the bat. That means the end behavior, since we have an even degree, is going to be either up in both directions or down in both directions. Now, we can note that the x to the 4th, the highest power out here, has a positive 1 in front of it. So since it's a plus 1 right there, we know it's actually going to be both in the up direction. Now, I get a little bit ahead of myself there because we do want to go back and try to factor our original problem to find those zeros. The only difference is this is no longer just a quadratic or a squared. There will likely be more factors, and there will definitely be more zeros, but the factoring techniques are a little different. In the last week or so, in section 3.3, you likely were introduced to the difference of squares, and that's what this one is going to need. So if I kept going, this breaks down again into x plus 3 and x minus 3. You can see how now I definitely have more of the factored look like my last problem did, so I could graph it. I'm going to first look for the 0 of this first one. I know that if I put in a -3 there, it will give me a 0. I also see that if I put in a +3 here, I will get another 0. But this last one's a little tricky. We can't just ignore it because it's not simple like the other ones. We need to think what number squared added to 9 would be 0. However, the tricky part is there isn't one, or there at least isn't a real number that would do such a thing, because a negative times a negative is always a positive, so squaring something will never become a -9. So in order to solve this, I'm going to leave my x squared there and subtract the 9 from both sides. Then I'll continue solving in an algebraic form here by square rooting both sides, and that leaves me with x equals plus or minus the square root of -9. Don't forget, when you're solving for x, when you take the square root, you have to have the plus and the minus. Now, this takes us back to topic 2, where we need to remember that the square root of 9 we were okay with. That's 3. But the square root of -1 is what we call I. It's an imaginary number. You can't technically take the square root of -9 on a calculator because it's not a real answer. Here, we have our imaginary or complex solution. And don't forget, there's actually 2 solutions there. We've got x plus 3i, or x equals plus 3i, and x equals -3i. So there are 2 complex zeros right there. And there they are. Okay. How many real zeros did it have? Well, we put 2 of them on the graph there. There was a -3 and a +3. So my total number of zeros is 4. It is no coincidence, and it is very true to say, that the degree of any polynomial should be equal to the total number of zeros. We like it when they're all real, but that's just not always going to be the case. Sometimes you need to do a little bit more solving, like we did here with x squared plus 9, to find those other zeros. They may be non-whole number zeros at times, or they may be complex and imaginary. It could also be possible that you would have to use the quadratic formula for some of your final factors. So to finish off our graph over here, we only have 2 real zeros, and we know it's going to finish in the positive direction coming off both of these zeros. But what happens in between there? If you graph this on Desmos, you'll get kind of an interesting thing. We know the y-intercept is -81, and for space purposes, I'm just going to write that that's what that is there. When you come down on that graph, or you look on Desmos, it actually kind of does what we would call like a flattened out version of a parabola. So it has a similar look to a parabola, but it's definitely a little bit flatter at the bottom. So I'm going to trace over here a little bit better in pink maybe. We want to, it kind of flattens and lingers. Again, I recommend you check it out on Desmos kind of to see that it doesn't really like make a straight line per se, but it definitely delays itself in returning. It's not a point. It's not like a parabola. It's just a little bit more of a flat turnaround. That right there is going to indicate that we have another imaginary zero there. It just behaves a little differently. So for this content, you want to remember that the degree will always equal the number of zeros. Factoring is going to help you reveal the exact location of those zeros. And you may need to use like solving for x or that quadratic formula to help finish finding the zeros if you can't factor all the way. That will especially happen when you're looking for your complex zeros.